welcome. This is the last seminar of the semester. I remind you, there is a social event tomorrow for the center. For those who want to come, you need to email us and bring your ID card with you, because wine will be served to adults. Seems nobody's drinking wine these days. All right, so we're very pleased to have Dr. Habib Najm from Sandia National Laboratories from Livermore, California. He's a chief scientist working for many years, most probably before even me, I would assume so. So people can extrapolate ages here. Has worked on all aspects of uncertainty quantification that you can imagine, from forward problems, inverse problems, Monte calibration, etc., and mostly with emphasis in computational chemistry and combustion. So today he will be speaking. I don't see that sign with uncertainties. It's an interesting sign. It's a logo of something. What is it in Japanese? What is it?
It's one of the LaTeX fonts.
The LaTeX fonts, okay.
I use it for the first character.
All right. So it's uncertainty quantification in computational models of large-scale physical systems.
Okay, thank you for the introduction. Thank you for being here. I work at the Combustion Research Facility at Sandia National Labs in Livermore, California. We've worked in uncertain quantification since about 2000. And we were driven to UQ from physical arguments in computing, computational modeling of combustion, and comparing to experiments. And so my focus is always on the applied side of the picture and dealing with difficult computational problems for large-scale physical systems. And I'm going to go over the general picture as we see it today in terms of workflows that are practical, that allow you to solve problems at large scale. And I will go over the formalism a little bit abstractly first in terms of the algorithms, and then I will go over that again in a particular context of an application. So I want to acknowledge funding from the Department of Energy across a number of offices, as well as DARPA and internal Sandia programs, and collaborations with a number of people that you see listed up there, as well as others. I will go through a brief introduction and then cover these topics listed here. I will talk about polynomial chaos smoothing and its utility in global sensitivity analysis. I will talk a little bit about sparse regression, multi-level, multi-fidelity methods, and then I will sort of discuss all of that in the context of this Scramjet application. Okay. So first, why are we needing to do UQ? Uncertain quantification is relevant in a number of contexts, whether you have an engineering context or a scientific context or a decision support context or an optimization. There's a number of motivations that I list up there for doing UQ, for being able to make predictions with uncertainties that are meaningful and that are useful to making decisions. If we're making predictions to be used for decision support, we had better have some confidence on what we're presenting to the decision maker. So there's a number of causes, needs for doing UQ. We come to it primarily from the context of validation and scientific perspective. So if you're simply doing computational science, and perhaps the word simply is misplaced there. If you're doing computational science, you're used to this picture where you have a model, you build a code to solve this model, you have the inputs that you get them from wherever you get them, papers or literature or your own measurements, and then you produce an output. And it's often the case that in the computational science world, that's the end of it. Now you go to the next model or the next biggest code. But the important way in which UQ comes into the picture is when you ask questions about where does the information come from that feeds into my model. Where do these parameters come from? They come from some measurement. And the active measurement relies on data. It's solving an inverse problem based on data. And since data is noisy, your estimates of these parameters will be uncertain, however you represent that uncertainty. Here I'm representing it for illustration as a probability density function. And therefore the output of your computational model will be uncertain, right? So uncertainty becomes part of the computational science enterprise. You need to be able to account for uncertainty, and it's driven from the fact that you rely on data. The data doesn't agree with your model entirely. There is both error and bias in both your model and in the data, and there's noise, of course, in the data. Another place where UQ comes in is once you're done computing things, you want to compute again and compare to data. And so making sense of your predictions of some output of interest, again, has to be done in the context of noise and uncertainty. And so UQ has to be part of the computational science enterprise. It's all over the place there. We talk generally about two kinds of UQ problems. There's the forward UQ problem, where we come in with some input uncertainty and we want to propagate that to the output of the model. And really, without going into any of the many details in that problem, you can think of this as the simplest thing you want to do is Monte Carlo. You have a probability density on the input, you want to generate random samples, and you want to see what the density is on the output. And of course, we know Monte Carlo is robust, it's very powerful, but it also has slow convergence in terms of convergence of the error is only as 1 over square root of n. And so, in fact, just about everything you can think of that's happened in forward UQ over the past 20 years or so has been about building a cheap surrogate for the forward map. That's essentially what it's about. And then you could use that surrogate to predict uncertainties directly, or you could use now Monte Carlo to do whatever you want. And building that surrogate involves a lot of different technologies. There's collocation using interpolants, regression and fitting, and there's a lot of work on Galerkin methods and polynomial chaos methods. I'm not going to go into any of that with detail, but I'm just presenting a big picture. And polynomial chaos methods are nothing but a generalized Fourier series that you use to represent random variables. And you build a representation for random variables as a function, and in that functional representation, you use a generalized Fourier series that has coefficients, as well as a basis that's a function of some simpler set of random variables. So that's all I'm going to show about that. How do we use it in UQ? You build a representation for the input that's uncertain using polynomial chaos. In other words, you have some input parameters that are uncertain, you have some density on them, you represent them using polynomial chaos, and now you have methods to propagate that functional representation from input to output. So y equal f of x, you go from x to y, and you build the representation for the outputs. Why is this useful? Because in many problems you can do this much faster than you can do direct Monte Carlo. In many other problems you can't, and so you have to be careful. Dimensionality matters. And once you have this, you can use it to estimate all kinds of moments that you might be interested in. Okay? So that's all I'm going to say about the methods for forward UQ. These methods can be applied in real problems. This is an example of UQ in large eddy simulation of turbulent bluff body flames. This is work with Joe Offerline, who was at Sandia. He's now at Georgia Tech, as well as co-workers, Mohammed Khalil, who was working with me, and Guillaume Lacaze working with Offerline. So this is a methane hydrogen jet at, you see a Reynolds number 9500, large eddy simulation of the computational geometry, ends you with something like 12 million mesh cells. This was solved on a 1,000 core machine, and you can see the run times indicated there. This is not a small computation. Here we had 3 uncertain parameters. These 3, doesn't matter what they are, but they're part of the computational model. If you know this Magarinsky constant, that's in there, as well as the turbulent Prandtl and Schmidt numbers. And using second-order constructions for polynomial chaos, we were able to do this with 25 samples only. 25 sparse quadrature points can give you a relatively good, accurate estimation of the output uncertainty. Here, the output uncertainties we're interested in had to do with profiles of the velocity field. And you can look into sensitivities and what's important for the uncertainty in the profile of the velocity field. Okay? So with relatively small number of samples. Here's another example, work with people at the University of Miami. And this is predicting Hurricane Ivan conditions over the Gulf of Mexico using the HICOM ocean model and looking at specific aspects of ocean modeling that were of interest. And there were 4 uncertain parameters. In this case, they had to do with the aspects of the subgrid mixing as well as the wind drag on the ocean. And here we had to live with order 400 runs. Okay, but still this is doable. This is not tens of thousands of runs that you might need to get accurate samples. Okay, so these methods are useful in large problems. But one of the biggest challenges in doing this is high dimensionality. These problems have 3 or 4 parameters, and you could afford to do second and third and fourth order expansions. But if you go to 300 and 400 parameters, immediately you have a major problem. And in that limit, directly, without doing anything, you could not do these problems with PC methods. You had to rely on Monte Carlo. But of course, the errors from Monte Carlo are not small either. It's just that you can get answers with as many samples that you can afford. So high dimensionality is a major problem in forward EQ, and it comes up in any sort of large-scale physical system that you might want to look at. If you directly apply sparse quadrature for solving these problems with polynomial chaos, you cannot do this because dimensionality is too high. One of the great advantages of Monte Carlo is that it's true that Monte Carlo convergence rate, the estimate of the error, the convergence rate, is independent of dimensionality, but the error in Monte Carlo, where the slope, the level of the slope, does depend on dimensionality if those dimensions are important. But the beauty of Monte Carlo is if there is a small number of parameters that matter, and you don't know which ones they are, but you know it's small, Monte Carlo can still find good estimates quickly without knowing which parameters are important. And so this is the one advantage we have in dealing with this problem. Before you go to polynomial chaos and quadrature, you have to start with Monte Carlo to discover the small number of parameters that matter. Of course, I'm assuming there's a small number of parameters that matter. And in most physical systems that are operating under normal operation, there is a small number of parameters that matter. If in order to fly an airplane, you had to control 1,000 knobs, that would be quite a problem, and you wouldn't be able to fly an airplane. There's a small number of things you have to control. And in many physical systems, a small number of parameters matter to smooth outputs under normal operating conditions, okay? And so this is the trick that allows you to get going in these problems. So the first step for us always in big problems is do first global sensitivity analysis with Monte Carlo and cut down the number of parameters that you want to handle as uncertain. And now you can do PCE, sparse quadrature, to your heart's delight. Of course, this is feasible, but it's not easy, and I'm going to go into a lot of what goes into the first bullet there of using global sensitivity analysis. Okay. And this is a collection of items that you can do, and I'm going to revisit this a number of times. Okay. So we are saying that you can compute good sensitivity indices and be able to estimate what's not important, take them out of the equation, just in terms of uncertainty, using Monte Carlo. But that still can require a lot of samples for big problems. So you may not need 10,000 samples, but you may need thousands still. And so there are a number of other things that you have to do to be able to deal with this problem. First, we presume additional degrees of smoothness in the sense that we presume that a quantity that's uncertain, say any type of field quantity that's uncertain, can be represented using polynomial expansions on stochastic space. This introduces a degree of smoothness. In other words, if a system has bifurcation at the given value of the parameter, this wouldn't work. Yeah? But if you know that the system varies smoothly with parameters, then you can introduce this assumption that there is a degree of smoothness you can rely on. And the first thing we do is you process the Monte Carlo samples, not directly to estimate moments for sensitivity analysis, but you process them first to fit a polynomial chaos expansion by regression. And then you extract the sensitivities from the Pca expansion. This gains you about an order of magnitude in terms of accuracy of Monte Carlo estimates of sensitivities. And it's a very simple thing to do. Your same Monte Carlo samples. You don't need to do any different. Just don't process them directly, fit a polynomial, then estimate sensitivities from the polynomial. And if this is a concern, you can, of course, increase the order of the polynomial, see what degree of smoothness is sufficient. Yeah. Now, when you do this and the polynomial is high order, you have a lot of coefficients, and so we have to do this regression carefully. That brings in the use of L1 norms and compressive sensing, and I will show that. And then finally, for really big problems, this is still not enough. And that's where we rely on multi-level Monte Carlo methods, as well as multi-level multi-fidelity methods. And these methods, I will mention them a couple of times, but I won't go into detail. The basic idea is that you can do computations with a coarse model or with a fine mesh model. Of course, you believe the fine mesh model, but there's a lot of aspects of the solution that the coarse model still captures. And so you can capture coarse features of the solution from coarse mesh model, or alternately, low fidelity models where you've made approximations that are very fast. And then you can correct this and get the final answer, combining these computations with some high fidelity and high resolution computations. And this gains you, each one of those, whether fidelity or resolution, can gain you a significant amount of savings. And I'm going to show all of this in action. Yeah? But this is the big picture in terms of how do we get into the door to do UQ in really big problems. We have to do global sensitivity analysis with Monte Carlo to eliminate dimensionality. And we process the samples by polynomial smoothing with compressive sensing. And then the samples are not all high fidelity samples. They're a combination of low and high fidelity. Okay. And then after that, you can do the sparse quadrature or any other forward UQ analysis you want to do. So I will start going into some of these details, but one thing first is about the fact that whenever we're fitting these problems in order to fit these polynomials to extract samples, or whenever you're dealing with data in scientific disciplines, you're quite often dealing with limited, sparse, noisy data. In many other disciplines, the problem is big data. We have that in science too, in many places, but in many places in science, we also have the problem of too little data or too little information in the data. So we're always dealing with sparsity and the fact that you don't have enough information. And moreover, the data is noisy. And even when you get computational data, the results can be noisy because in many systems that are dynamical systems, the quantities of interest are statistics of the solution, and those you could not compute for long time to average. So your sample results from the computations, if you start moving parameters around, will be noisy, and you have to deal with this noise. Okay? And so these issues are important, and we have to deal with in this type of analysis here, and that's why we introduce compressive sensing. I have a couple of slides here that I won't go into any detail on, but let me move forward and talk about that as I go forward in time. So we're going to get to this picture where we're going to use samples, computational samples, to fit a polynomial to process the global sensitivity analysis results. And so this is, again, what I said, but now I'm putting the polynomial specifically here. This type of polynomial is our polynomial case expansion, and the CK coefficients are the ones you want to fit. So we want to be able to process samples and fit these types of polynomials to them when you have not many computational samples that you can afford to do, okay? And this is what this polynomial smoothing does. So if you look at this slide, what we're showing is the relative error in the sensitivity estimates you get. If you did this directly with Monte Carlo, is over this MC side. And if you use polynomial fitting and then extract them, that's here, okay? And so this is just a simple problem for dimension 1. And looking at 300 samples versus 1,500 versus 3,000. And what we're showing is on the left, the Monte Carlo estimates are, of course, getting lower error as you take more samples. On the right is the error extracted from the fitted polynomial, and whether you use first, second, third, or fourth order polynomial. And you can see that for all cases, you have about an order of magnitude improvement in the error. A very simple procedure. You go to 3 dimensions, you still find the same kind of performance, especially if you go to higher order, you have 2 orders of magnitude. And 10 dimensions, the problem is still there. So this is the saving that I talked about earlier, which is really a very simple thing to do, as long as you have some argument for smoothness. And this is certainly a very effective way of improving the estimate, the error in the Monte Carlo estimates. And then on top of this, I said we do sparse regression. So I want to talk a little bit about sparse regression here. What we're doing is fitting a function to some samples. So we have the function up there, and you have some n samples, and you're minimizing this norm, which is the fit of the function to the data. And the problem, of course, is that you can be in situations where the number of data points is smaller than the number of coefficients you need to find, and this is where you need to introduce some type of regularization. If you do optimization, you're familiar with that. And this is where compressive sensing comes into the picture. And I show this slide just to intuitively illustrate the effectiveness of compressive sensing and the L1 norm. So the regularization is done by adding some penalty term to the objective function that gives you the desired properties you want. So the first bullet up top shows the classical Tigonov regularization picture with the second order norm on the coefficient vector in the polynomial. Below that is the L1 norm, the absolute value norm, again on the coefficient vector. And there are a number of ways of applying it. You could reformulate the problem in different ways. And the value of the L1 norm in compressive sensing is the ability to discover a sparse model. And what I tried to show with the diagrams below is that idea, and just intuitively to illustrate it. So when you have an underdetermined model, in other words, you have too few data points, it means you have some null space, and you could fit any polynomial or any function that falls in that null space will fit the data equally. We're dealing here with functions that are linear in the coefficients, so that's why you have that straight line. And if you use the L2 norm, the unit ball is the sphere, of course. If you use the L1 norm, the unit ball is this rhombus that you see here. And insisting on a norm, on a value of the norm that's less than something or satisfies certain constraint you're after, requires that you intersect this unit ball with this null space. And you can see that in general with the L2 norm, you're going to intersect it somewhere where both coefficients, x1 and x2, these two axes, are non-zero. You're going to find some model that fits the data, but both parameters in this case, I'm looking at a 2D model, but you can think ND. Both parameters are live. But if you do this with the unit ball being the rhombus, you're going to hit corners rather than sides. And you're going to get many coefficients that are 0 while others are not. And you're going to be able to have a sparse model. So that's the value of using the L1 norm on compressive sensing. And you can do this in a Bayesian way, where you do the fitting to estimate a density on these coefficients. And I didn't introduce Bayes' rule, but it's up there, the first equation. And it provides you a density on the coefficients of interest, given the model and given any prior information that you have. And without going into detail, you can reformulate this regression in a Bayesian way, and there's lots of work on this in the literature. And there are priors you can use in the Bayesian formulation that are equivalent to the L1 norm. These are Laplace priors that use the absolute value of the coefficient vector. And without going into detail, I will skip over and just show comparison of Bayesian compressive sensing and compressive sensing, the native form. They compare similarly. In general, you can use which one you like. If you're interested in estimates of uncertainty in the fitted parameters, you could do this in a Bayesian way. Here we're showing the decay of the L2 norm of the error for different dimensionality with number of samples. Yeah? And for both Bayesian and L1 minimization and different order. I want to show this plot only, frankly. This plot shows the number of terms in the fitted model given a certain dimensionality and order. And here, for example, for 10-dimensional 6th order, you can see that the polynomial has 8,000 terms. And that's a lot of terms. But using L1 norm regularization, you're able to fit models that generally stabilize. As you take more measurements, you're not increasing a lot the number of non-zero terms, where the number of terms is order of 100 or so. Yeah. So out of the 8,000, you're able to pick a very sparse model that fits the data. And that's the valid utility of sparse regression when you have too few data points. You cannot take tens of thousands of data points. Okay. And then the last part of the picture, as I said, is the multi-level multi-fidelity. So again, what we do is we do PCE fitting as a first step with GSA samples. We use the L1 norm to do that fitting to get a small number of coefficients that are non-zero and get robust fitting. And this is great, but we need more in order to cut down the number of high-resolution, high-fidelity runs, and that's where multi-level multi-fidelity methods come in. And I've said all of this before. In words, we use as many low-resolution, low-fidelity computations as we can, as long as they have some correlation with the high-resolution, high-fidelity model results. We can learn from them and bring the two together. And here's an example, again, without going into detail. On the right, you can see the curves for the error estimates with Monte Carlo is the top curve, with multi-level Monte Carlo is the blue curve, and then the red curve with multi-level multi-fidelity. So you can gain quite a bit of savings and get more accurate samples for the same number of computations. And on the left is just the error estimates for different number of samples. So in my view, multi-level multi-fidelity methods are crucial for being able to do UQ in large, difficult applications. Okay, and here's a large, difficult application. This is a Scramjet engine. A Scramjet engine is a special kind of jet engine designed for supersonic and hypersonic flight. It has no moving parts. There's no turbines or compressors. It requires another engine to get you up to speed and elevation, and then the ramjet or scramjet kicks in. The word comes from ramming the gas into that channel that you see under the wing there where the engine is. And when you say scramjet, it's because it's a supersonic combustion ramjet. So a ramjet engine essentially just starts going already, and then you turn it on, and then just the force of the air coming in mixed with the fuel that's injected burns and goes out the back and propels the rocket or plane forward. And here we were looking at studies of a specific scramjet engine design. This was based on an experiment done at NASA a while back, using large eddy simulation and doing estimation of uncertainty in this geometry. And the two graphs below are showing the simplified geometry we dealt with, and also the fact that the red part that you see is the half problem that we dealt with in order to be able to afford the simulation. And on the top right, you have the actual sample of predictive modeling or predictions in this system using large eddy simulation. I won't go into any detail on the LES simulation. I'll just have one slide on that. A lot of uncertain parameters. We have 24 uncertain parameters, and I won't go into any of them, but these are generally operating conditions, aspects of the design, the location of the injectors, the angle of the injectors, etc. And they have ranges that are understood from the literature to be meaningful ranges. Okay. So what code did we use? This uses this Raptor code that Joe Offline developed over a number of years, both at Stanford and at Sandia. And he's, as I said earlier, he's currently at Georgia Tech. I won't go into any detail about this, but suffice it to say it's a large scale computational type of code. It has scalability on very large numbers of cores. You can see the numbers there, and it can be run massively parallel for very complex physical systems with, including complex equation of state, sprays, etc. Yeah. So here's examples of the computational results. What we're looking at here is a 2D system. Of course, we know turbulence is 3D, but for computations, you can always start with simpler versions of things to feel your way around. This is a 2D geometry of the system, and what we're looking at is this half geometry where the flow comes in from left to right. And the top picture is showing the temperature field. So you have cold air coming in, and where it goes over that cavity in the middle of the channel is where the flame is stabilized. As air comes in, it's mixed in with the fuel. The fuel is injected a little bit upstream of the cavity. Somewhere up here is a fuel injector. And you can actually, if you can see that, there's a shock wave at that location. You can see that in the temperature. You can also see it in the Mach number right below it. There's reflecting shock waves off the wall. And this flow ignites and burns and goes out the back, and it's a simulation that keeps going on and on. And so you can compute this, of course, with a lot of difficulty, but you can compute it. In this case, we had ethylene fuel, so that's the C2H4 mass fraction is the third plot, showing you the structure of the ethylene, and then CO and CO2 further below. Okay, so it's a turbulent flow with injection of liquid fuel at supercritical conditions. You have spray at supercritical conditions, and mixing and combustion with this combustion mantle. Okay. This is an example of a particular mesh resolution. We call that D32, which means you have 32 mesh cells within the aperture of the injector, which you cannot see, but it's a It's a small aperture upstream of the cavity. There's a second injector downstream of the cavity here. Okay. And this is the 3D computations of the same. We're showing here a cut at the location between two injectors, because you have, in 3D, you have injectors at different planes. So this is at a certain location. Again, you have these flow structures, you have the shock waves, and this is another cut at the injector. And you can see these pictures are actually small, but you can see here something earlier upstream. That's the flame sheet starting from the injector and moving further downstream. So these are big simulations with high resolution and complex physics. And we want to do this whole game with this, right? So I'm going to apply the methods that I talked about earlier. So first, global sensitivity analysis. Right? You might know global sensitivity analysis. It's essentially you are looking to see of a number of uncertain inputs to your model, which of them contributes the largest contribution or the important contributions to the uncertainty in the output. You're looking for fractional contributions to the output variance. And this is here is an example of one sensitivity index, as they're called. And you can formulate different kinds of indices. I won't go into any of the notation. But the important thing to look at is that you're computing conditional expectations. And it can take quite a bit of samples to get conditional expectations. That's why all of the material I talked about earlier of how do we get global sensitivity analysis results that are reliable when we cannot take too many samples. And so this is where we're going to start applying the Pca regression and then the L1 norm constraint and multi-level multi-fidelity. So again, the Pca regression relies on fitting a polynomial chaos, so a polynomial chaos expansion. So this is again the PCE up there. Again, the function coefficients. C is the vector of interest when we do the regression. And we have some set of parameters that are uncertain, this lambda, and then we're after this coefficient vector C. And once you're done fitting the polynomial with these samples, you can evaluate the sensitivity indices directly. So here, for example, this ST index is just the sum of the square of the coefficients appropriately normalized. Yeah. So you can compute these indices directly once you've fitted a polynomial. And that's what we do. So we have the polynomial regression, and as I said, we want to do this using L1 norm constraints to facilitate this. And because we're doing it with large computations here, we need to do that. So in this case, if you simply fit the PCE, and we have 24 dimensions, you're going to get on the order of 3,000 terms in the PCE expansion. So that's a lot of terms to estimate from some hundreds of samples. So this is why we use L1 norm constraints and compressive sensing. So the formulation at the bottom is indicating the use of the L1 norm within the objective function when we do the fitting. So this is the term that's fitting the polynomial expansion to the computational samples, and this is the L1 term that is trying to drive us to sparser polynomials. Okay, and then the multi-level multi-fidelity picture on top of that. And so in this case, what do we do with multi-level multi-fidelity? From a multi-level perspective, it's obvious. We use different resolutions. So I showed before this D32 case where we have 32 mesh cells within the injector. We also do D16, D8. You get the picture. We're using coarser resolution computations as well as the higher resolution runs. So that's the axis of multi-level here. That's resolution. And then at the same time, we have access to different model fidelities. So you can do different kinds of approximations in large area simulation. You can rely on dynamic models versus static models. But in fact, the cost difference is not huge, at least in this application. In this case, we actually used a combination of 2D models and 3D models. And of course, a 2D model is not going to give you any accurate representation of 3D flow, turbulent flow. But if you think of the bulk flow features, the 2D model will get you information on the bulk flow features that are correlated with what you get from the detailed model. And that's all you need. You don't need it to be accurate. You need to be correlated with the detailed model in terms of its performance as you change parameters. And the multi-level, multi-fidelity idea is to fit these polynomials that I showed earlier with regression, fit them combining information from different levels of computing. Yeah, and so this sum that you see there, called telescopic sum, is computing a correction onto some fitted polynomial per each level of modeling. Yeah, and so there's a lot of literature on multi-level, multi-fidelity methods. In fact, there's quite a bit of literature today in the UQ literature that you can find on these. You can look up. Okay, so that's the picture we ended up with, right? We are doing global sensitivity analysis with Pca regression, and here we're relying on both 2D LES, 3D LES, as well as fine grid and coarse grid computations. And of course, the important question is, what are you after? What are the quantities of interest? And so here, I'm listing on the right a number of aspects that you can imagine you need in this flow. Statistics of the turbulence, stagnation pressures, any aspects of propulsion that are significant in this problem. Okay, and in this case, you can see down below what we used in terms of runs. We had, in terms of relative cost of runs. So for one 2D coarse resolution computation, that's equivalent if the cost of one 2D is 1, then the corresponding cost of the 3D coarse resolution is this much, and 3D high resolution is 2,000 times more, right? So the cost differential is huge, and so if you have any correlation of these low resolution computations with the high resolution information, you will gain. And here's an example of what we get, right? So we do all of this. In this case, we relied on some 220 simulations to do global sensitivity analysis, a mix of different resolution and different fidelity. And we get the GSA results below, where we've plotted these indices that indicate importance versus each parameter in the problem. And without going into all of the parameters, what you can see is important to these outputs of interest, such as combustion efficiency, our T0 and M0. This is stagnation temperature, stagnation Mach number. If you know combustion and flow, this is, of course, quite expected. The turbulent Prandtl number shows there for some version of things, but these are the two important things, T0 and M0. So you know what's really driving the uncertainty in combustion efficiency. And if you look at the stagnation pressure loss, you also see these two, but you also see on the far right that one of the design parameters is very important, and that's the second injector location. So where you put the second injector matters to the pressure loss in the system. Okay, so these types of information are crucial if you're designing a system like this, or if you're trying to understand the consequence of lack of precision in any aspect of the operation of the system. Okay, and when you do this analysis, you now can extract uncertainties. In this case, we're actually plotting uncertainties directly based on the resulting surrogate built from Monte Carlo, and we're plotting uncertainties here for temperature, pressure, and Mach number. And what we're actually plotting is the mean field as well as the standard deviation due to the uncertain parameters. And you can try to read some aspects of this. For example, you see that there is both significant value of pressure above the contraction, which you can expect from the redirection of the flow at the ceiling of the channel. Or well, it's not a ceiling, but this is where the two channels meet. This is a symmetry plane. Both mean as well as standard deviation are large there, and that tells you something. And you can see also that the mean of the Mach number is large up there, but a little bit of uncertainty in the Mach number at that location. But almost all the action is centered on top of this contraction in the channel. Okay. And you can also look at, sorry, the fuel is ethane, not ethylene, what I said before. Ethane as well as oxygen, carbon dioxide. Okay. So I want to discuss and close here. I sort of sketched over a broad landscape. I didn't go into detail, but I wanted to try and represent a little bit the workflow we are dealing with these days for doing UQ in very large scale problems. It's not at all easy, and you have to combine a number of methods and a number of algorithmic advantages you gain from different places. And the picture again is to do first global sensitivity analysis and make use of smoothing with polynomial regression, L1 norm, and multi-level multifidelity methods. And then you can go after this with sparse quadrature or otherwise. Now, if you have a problem where you have all the parameters are important, that's a very different situation. And when do you have that? Well, you have that when you either ask for something that you shouldn't be asking for, or you have some type of failure. The first case is if you ask for uncertainty on, say, the flow velocity at this instant in time, at this location in space, in a turbulent flow. Good luck. No one can do that, yeah, because the butterfly effect, yeah. Turbulence is a very nonlinear dynamical system. You lose correlations very quickly. Any epsilon error in initial condition will give you wildly different answers at a specific location in time and space. So from a UQ perspective, this is not a useful question to ask because there's no good answer to it. And this quantity is in fact very non-smooth. You couldn't represent it easily. It depends on everything. So you shouldn't be asking this question. You should be asking questions that make sense. In this case, it's smooth quantities of the turbulent field that matter to the design of any engineering system. And those quantities are, as I said, smooth. These are statistics of the flow. The other place where this comes up is failure. If you have fracture, let's say, in a solid rod, or some extreme event, those are very hard to deal with using this approach that relies on smoothness, because if you can imagine doing a stress test on a metal rod and try and predict exactly where it's going to break and what the shape of the fracture would be, good luck. Yeah. So these are dependent on very fine level details in the material structure that you could not predict, you could not measure or predict. Yeah. So if you move away from these types of scenarios, deal with smooth observables in operating systems that are smoothly operating, then these things are feasible. And then you can build a surrogate, you can do with it whatever you want, okay? There are other methods that I didn't discuss. There are methods for adapting the basis. So the polynomial expansion that I presented always used a specific basis. I was only fitting the coefficients. You could do better by adapting the basis. So there are basis adaptation methods, including active subspace methods, they're very similar, that you can use to gain further. And also, you can discover manifolds in the response of the system to the variation of the parameters using, for example, isomaps or diffusion maps. And when you discover manifolds, you see how things are correlated, you can also make significant gains in exploring the space. So I didn't discuss any of this. And I would present a caution that computational results from turbulence or any type of dynamical system are going to be noisy if you are in a large-scale computational setting, because you cannot afford to take hundreds of flow-through times in the system to get very accurate statistics, say, of RMS profiles. So you have to deal with noise in this problem. And the last bullet is sort of indicating that you could use other things than polynomials. All we use the polynomials for is to say there is some degree of smoothness. You can use other things, right? So you could use local interpolants. You can use Pca approximants for certain cases, radial basis functions, Gaussian processes, neural networks, you name it. Yeah. So there's a lot of work on many different kinds of representations. Okay. And I will end with this announcement. There are two meetings that I would like to call to your attention. One is the second workshop on machine learning and UQ. Both meetings are at USC in LA. This machine learning and UQ workshop, this is the second time. We did this last year, and it was a very successful workshop. And it's seeking this interdisciplinary space between UQ algorithms and methods and machine learning algorithms and methods, and cross-pollination from both sides. And the other is the UQ Summer School at USC. This is the seventh incarnation of this. It's been going on for a while. It's been quite successful, and again happens this summer. So July and August. The summer school is essentially open for just attendance. The speakers are set. The workshop is open for submissions of abstracts. And so I encourage you to look at both meetings, and the web page is there. With that, I'll end, and thank you for your attention. Yeah.
I enjoyed it very much. I have a question on the mixing of these multi-fidelity, multi-scale, because you would want to know in advance how many of big 3D you need to do and how many small 2D you can do, because if you do 10,000 big 3D, you already did them.
Right. So
and
so
you don't know in advance how
right.
to choose, how to mix, how do you mix.
Yeah. So the question again is, how do you choose how many high fidelity and how many low fidelity runs to use, or low resolution, high resolution runs to use? So there's an adaptive strategy to do that. You can judge on whether the low fidelity computations are at all useful or not first, because you're going to do some high fidelity, and then you can do low fidelity and see if there's correlation. So there are very quantified measures of correlations as you take low fidelity samples. And as long as you're finding that the samples are informing you on the quantity of interest, they're adding information, you keep doing that. So there is a recipe that you could see in the literature on defining how many low fidelity samples you need to get the information you want. And if you have no correlations, and in fact in this problem we initially did D over 8 and D over 16, and it was not enough. It was really not, D over 8 wasn't informative on things that were relevant in the flow. So we had to go to D32 to get the D16, D32 combination to be informative. So when that happens, you have to change what you're doing. You have to pick scales where there is some correlation. Yeah. But if you're stuck in, if there's no correlation, you're stuck. You can't use these methods. Yeah. So if there's no information that's useful from the low fidelity model, then there's no point in it. Yeah. But there's a test for that. Yeah?
With 24 input data, how do you take care of the unstart phenomena, which is caused by the choking in the combustion?
Sorry, repeat the question again.
With the 24 input data that you're having,
Yes.
How do you take care of this unstart phenomena that's caused by choking in the combustion? Because if you vary those parameters, it will cause the choking in the combustion, and then your efficiency decreases. So how do you take care of those? Like when you're doing the simulation?
You're saying choking in the
Yeah,
combustion?
choking in a combustion.
As in the dynamics of the combustion
Yeah.
system?
Yeah.
Okay. Right, so the question is about dealing with the effect of parameter variation on the dynamics of the combustion system. And you can get under regimes where, you know, the engine is not operational as you like. Right? So this is something you have to watch out for. When this happens, you have the problem that I alluded to before. We have bifurcations. In other words, the system behaves in an entirely different way. There's no smooth variation of the parameters. Yeah? And then you have to do something. So what you can do is you can say, my range of uncertainty was too generous. No, obviously I don't want to consider uncertainty in this region. I was silly, right? You can update your information. But if not, if these uncertainties do exist like that, then what you have to do is deal with the system on either side of this discontinuity separately using local PC methods, right? And this can be tricky in high dimensions because you have to discover where this shock is. Shock as in discontinuous behavior in parameter space. And that can be very tricky. You have to do that. Otherwise, you don't know where to discretize the space and build the smooth polynomials. So you can do two things. You can either simply rely on Monte Carlo, forget the smoothness, and live with Monte Carlo. And you can do multi-level Monte Carlo, right, without the PC smoothing. Or somehow you discover this region in space and do a discretization with polynomials on either side of it. Yeah? And as I said before, this can be hard, especially in high dimensions. In high dimensions, what we have done before, we had a problem that was in 80 dimensions. This was a climate model computation. And we knew there was some discrete shock like that in the slope of the solution, somewhere in ATD. But we could not imagine that you could take enough samples to locate and parameterize this, subspace where the parameters have this behavior. So instead we used the classification and clustering using random forests, because what you can do is you have a situation where on the left side or somewhere in this region you have one type of polynomial, and on this side some other polynomial, right? You just need to decide which side you're on. And so what you can do is take many samples and cluster the data, and then you have a classifier that if I come with any new sample, chooses which cluster it's in, and therefore chooses which function I want to apply. Okay. This works in the region of the discontinuity. You have 10-15% errors. It's not as good as actually parameterizing the curve where the shock happens. But this in high D is the only thing I know to do to get the two different behaviors represented, other than just simply Monte Carlo. Other questions? Yeah.
You often mention that having sufficiently high smoothness in the response is important.
Yeah.
How in practice this is basically determined? So how in practice do you know that, and how much you have to sample to know that? I mean, is there any?
Obviously, it depends. So the question is, how do you decide on the degree of smoothness that you can expect to make use of? This is now about the specific problem at hand. You have to know your problem, of course. If you know you have this type of behavior with choking, you have to declare smoothness is dead, and I need to figure out what I'm doing. In general, you can look at diagnostics. Obviously, if you're fitting the data with a polynomial, and as you increase the order of the polynomial, you start finding the Runge phenomenon. You know you have a problem. Yeah. In principle, you have to consider diagnostics like this. You expect that if you have smooth behavior, and you increase the order of the polynomials, you're going to see some spectral convergence of these representations. That's what you look for. And if you don't see it, then you have to back off and figure out the source of the problem. Yeah. But from a physical argument, you say, if I know my physical system, it's behaving in a certain way, and over this range of parameters, I know it's still behaving. This flow is laminar, and it's laminar from Reynolds 100 to 300 of interest. Then you know. Yeah. But if you start going to regimes that you don't know the physics of the system very well, then you have to rely on these convergence diagnostics to figure that out. Yeah. Okay.
Well, if there are no more questions, thank you very much for coming.
Thank you.